All right. Okay, so let's get started with the activity questions. Here you see, okay, yeah, so here you see the questions, the first set of activity questions.
No, I can't.
You can't see, is it?
Your screen is.
One moment, one moment. Oh, one moment. Okay, can you see this?
Yes.
Yes, ma'am.
Okay, all right. Okay, so here you see the first set of activity questions. I hope you've watched the videos so you'll get some idea of these questions. So let's go over them. There's some configuration issue here. So it's nothing but, I hope you can see this is just this thing, and less than, this one is greater than 0, and this is less than 0. It's all okay. So I'll get this fixed after the session. Okay, so what's the question? There is a model which transforms a d-dimensional data point to either +1 or -1. And the model is such that it takes the sign of W transpose X. Now we are asking which of the following are equivalent to this. So what exactly is this? This is an indicator function which gives you 1 or true, which gives you 1 actually when this is true, right? Which means when the output of the model for the given data point X is not equal to Y, which is the actual target, then this will return you 1. Okay, so this is a 0-1 loss in particular. So we are asking which of the following is equivalent to this. Okay, now the model looks at the sign of W transpose X. Okay, if we are not looking at the sign of W transpose X and we are simply multiplying this W transpose X with Y, and Y is one of the values between out of +1 or -1, then what will happen? Yeah, so W transpose, what we are seeing is W transpose X and Y, right? These two things we are checking. Y can be either +1 or -1. And we are not seeing the sign of W transpose X. We are just multiplying W transpose X with Y. Now, let's say this is positive. If this is positive and this is also positive, then this multiplication will be positive, right? If this is positive, sign is +1 and that matches with Y. So there is no error, right? And if it is negative, this is also negative. Their multiplication will be positive and no error in that case also. The error will happen when this is positive and this is negative, right? Then their multiplication will be negative. Then in that case, there is an error. Another case would be when this is negative and this is positive, then multiplication will be negative and there is an error, which means the error will happen when this multiplication is negative, which means when W transpose X into Y is less than 0, then error happens. And in that case, we should give 1. The indicator function should give 1, right? So that's the equivalent story. So that's what we are asking. See, h of x is equal to sign of W transpose X. If you are not looking at the sign, you're just multiplying W transpose X with Y. The error will happen when the multiplication of W transpose X and Y is less than 0, right? So that's what we saw, less than 0, right? This very thing. So the fourth option is the correct one. I'll get this fixed.
Ma'am, I have doubt in activity 11.4. Could I ask here?
11.4. Okay. Can you post on discourse regarding that? Nitin will take care of that.
Okay, ma'am. Yeah. And one more thing, ma'am. In lecture 11.3 also, in case 2, I think that epsilon I equals to 0. I think that is some problem there.
In the lecture, there's a problem?
Yes, ma'am. 11.3, case 2.
11.3 lectures, is it?
Yes, ma'am, it is.
Okay. Can you post on Discord so that we check that out and we'll get that fixed if there is a problem?
Okay, okay. I just need an explanation there.
Yeah, we will explain over discourse regarding that on week 11. Okay.
Okay, okay, ma'am.
Okay, so getting back to this one. So whatever we just understood, that's precisely the 0-1 loss. So 0-1 loss can be either written this way or it can be written this way. That's what we saw. W transpose X is less than 0, then there should be an error of 1. And in the case when W transpose X into Y is greater than 0, which means it is positive, that positive comes out when the sign matches, okay, which means when there is no error. So in that case, we will give a penalty of 0. So that's precisely your 0-1 loss. Now, out of these three, we have to choose which one represents the 0-1 loss. Okay, so does the first one represent that? On the x-axis, we have gx into y, where gx is equal to w transpose x. Okay, so basically the x-axis is w transpose x into y. So here, w transpose x into y is greater than 0, right? Here, after this point, w transpose x is greater than 0, and in that case, there should not be any error. And when w transpose x is less than 0, which means it is negative, which means there should be an error of 1. That we should note. So the first one is incorrect, second is incorrect, the third option is the correct one. This is your 0-1 loss. Greater than 0, there is 0 loss. Less than 0, there is 1 loss. Right? That's how your 0-1 loss is. Is this point clear to everyone? Okay, I hope this
Yes, ma'am.
Okay. All right, so next one, 0-1 loss is a continuous function, but not convex. Is it a continuous function? So this is in front of you, as you can see.
No.
There is a break here, right? So this is not a continuous function. So the correct option will be false. Now, in the lecture, sir discusses that since 0-1 loss, which is the most natural choice of a loss function for a binary classification problem, is not continuous, we need to look for surrogate loss functions which are continuous as well as convex, right? So in that attempt, we are looking at different error functions. One of the functions that we are looking at is squared loss function, right? As we know, in regression, we use squared error, and we know that that's a continuous as well as convex function, and hence we can happily apply gradient descent on that. We can happily get the global minima. So we are arguing, can we apply a squared loss here in case of classification, right? Can it work as an appropriate surrogate loss function or not? So there's an explanation in the lecture, probably, I don't know you've seen that or not. So I'll just go over those slides to explain that very concept. So whenever we use squared error for tracking the loss in case of classification, this is the kind of plot that we get, right? This is the kind of plot that we get. As we can see, this line is a 0-1 loss, right? As we can see, there is a 0 error in this region, right? In this region, we have just now seen when gx into y is greater than 0, which is positive, there should not be any error. But the square loss is giving us a huge error. When w transpose x into y is equal to 1, there is a 0 loss, which is correct. This is also incorrect if you see. Even in this region, 0-1 loss says that there should be 0 error. Why? Because w transpose x into y is greater than 0, positive it is. This is still fine, it's low. But here in this region, you see this is huge. So even when there is no mistake that the classification algorithm is making, squared loss is giving a huge error. due to this reason, squared loss is not an appropriate surrogate loss function for 0, 1. So the correct answer will be false. Yeah. Next option, next question. So it's a continuation of whatever we just now discussed. Squared loss represented by W transpose X into Y minus 1 square may not be a good loss function. Why? L is not convex. No, this is untrue. This is false because L is actually convex, right? L can only be used for linearly separable data. There's nothing like that. So this doesn't make sense. If sign of W transpose X is not same as Y, L will produce a zero loss.
False.
That is incorrect. So if sign of W transpose X is not same as Y, which means, so if the sign of W transpose X is not same as Y, then what will happen? W transpose X into Y will be negative. Negative minus 1 will be negative. Square of negative will be a huge quantity. It will not be 0. So this is also incorrect, right? Last one. If the sign of W transpose X is same as Y, which means this will be a positive quantity, L will produce a huge loss if W transpose X is not equal to 1. So this is a huge quantity. Positive, positive, negative doesn't matter because it's a huge quantity and we are just subtracting minus 1 and then squaring it up. So this is going to be a huge quantity even if the sign matches. The only point where it will be correct is when W transpose X into Y is equal to 1, right? So if you look at, sorry, yeah, if you look at this, in this region, what is happening? W transpose X into Y is equal to 1. Okay, in that case, you put 1 here, 1 minus 1 is equal to 0, so squared loss comes out to be 0. This is correct, but all this region is not correct. So that's why this squared loss may not be a good loss for representing 0, 1 loss. Okay. All right. Let's move on to the next set of questions. Okay. Which of the following is true with respect to regularization in SVM? Now, SVM, if you remember the loss function in SVM, it was like this, where this particular part is called hinge law. So if I write it here, so the loss in case of SVM, what is that? Square of L2 norm of W, half of that, plus C into this quantity, which is precisely your hinge loss. This is your SVM loss, okay? SVM loss, this equation represents your SVM loss. Now, this particular term is what is doing regularization here. Now, what are we asking here? What is the relation between regularization strength and C, right? Now, if you remember regularization in linear regression, there was sum of squared error, linear regression, sum of squared error, plus there was this regularization term, there was lambda, and then this term was there, right? This term was there. Now, this lambda was regularization strength. If you increase, what would happen if you increase the value of lambda? Can you tell me?
This length of W square will decrease.
Right? When you increase the value of lambda, then the strength of regularization increases and the length of W further reduces, which means regularization increases, and regularization is directly proportional to the value of lambda, right? Now here, this is the scenario. The C term is not here, but over here. Now let's say I divide this by, let's say I have, I do divide by C, let's say. So it will be something like this. This will become 1 and this will become 1 by C. Now, if you see the relation between regularization strength and C, right? So when C is increased, what happens? This 1 by C reduces, isn't it? When C increases, 1 by C reduces, which means the regularization strength reduces, right? On the other hand, when C increases, this whole thing reduces, and hence the regularization strength reduces. So in case of SVM, the regularization strength is inversely proportional to the value of C, right? So this is something that you might want to note. In fact, if you see the sklearn implementation of SVM, there also you can see there's a parameter C. So whatever parameter C that we were talking about, this acts as a regularization parameter. So in linear regression or in ridge, we have lambda. Actually, we have alpha there, right? The regularization strength is represented by alpha there. So here it is C, and if you see, the strength of regularization is inversely proportional to C. Okay, that's what that's the point I was trying to make. Okay, so getting back, yeah. So the correct option will be regularization strength is inversely proportional to the value of C, this one. Which of the following is the best convex approximation of the 0-1 loss? So just now we discussed that squared loss is not a correct approximation of 0-1 loss, because it gives a very huge, it gives a huge value even when there is no mistake. Absolute loss, as we know, it's not differentiable, right? So this may not be a good choice. Then hinge loss, we have seen it actually approximate decently. So if you see this one, this blue, dark blue one is your 0-1 loss, and this orange one is your hinge loss. Okay, so here it's actually matching. Here, where there should be this much error, this much loss, hinge loss is giving this much loss, that is fine, but here it is matching. The only problem that is happening in this particular case. So that's why we are saying that it's an approximation. It cannot exactly represent the 0-1 loss. So only in this particular area there is some mismatch, but here it is matching. But it's a decent approximation, right? That's why we use it, because it is continuous. So hinge loss will be the correct option. Next one. Hinge loss is a good surrogate function for 0-1 loss. Hence, the loss produced by hinge loss will be exactly same as 0-1 loss. So I just now showed you that it is not exactly same. For some cases, it is exactly same, but for some other cases, as I showed you, it is not exactly same. There are few differences. So the correct option will be false. Okay, next one. Logistic regression. We have seen the loss that we use in logistic regression. Which loss do we use in logistic regression? Anyone would like to answer that? Okay. So in logistic regression, this is the loss that we use. So this is binary cross entropy, basically. Yeah, so, okay, let me write this down in an easier form. So we have some y, right? This y is actual y, and the model is predicting some y hat, okay? And these y hat are probabilities, if you remember, right? We apply on W transpose X, in case of logistic regression, on W transpose X, we apply this sigmoid function, and that results into, that compresses the value of W transpose X somewhere between 0 and 1, right? And that's used as the probability for that particular data point X. So that results in y hat value. Let's call it y hat, the predicted value, and y is the actual value. So we want to compare it with the actual value. So in case of binary classification problem, so minus y log y hat minus 1 minus y log 1 minus y hat is precisely what we use, right? This is binary cross entropy. So please note that log is used for y hat. Now, what are the values of y and what are the possible values of y? So the possible values of y are 0 and 1, right? So this particular formula is used when y is represented as 0 and 1. I mean, the positive class is represented as 1 and the negative is represented by 0, right? So when y is equal to 0, this whole term becomes 0, right? This y becomes 0. So we are left with this particular part. So when y is equal to 0, we use this. And when y is equal to 1, this term becomes 0 and we are left with this particular part, right? So that's how, so this is a combined formula, you can say. All we are doing is we are, negative sign and then the actual y value and then log of predicted y value. This is all we are doing for each class, right? For each class we are doing this and we are aggregating that. In case of binary classification, there are 2 classes, so this is what we are using. A generalized form, if you want to know, that is cross entropy loss. So this one is binary cross entropy loss. The generalized one is cross entropy loss, where if there are 3 classes, there will be 3 such terms. If there are 4 classes, there will be 4 such terms and so on, right? That's a generalized one. Okay. So this formula is used when y can be, y is represented as 0 and 1. And I told you when y is equal to 0, we use this. When y is equal to 1, we use this. This term becomes 0. So when we actually expand these 2 things, so this is the first case. Okay, one more thing. What is y hat? In case of logistic regression, what is y hat? Y hat is sigmoid of W transpose X, right? And what is sigmoid? 1 over 1 plus e to the minus W transpose X, right? So you can expand like that. So that's what we are doing here. When you expand this sigmoid, you get this, and ultimately you get this formula. The other case, right, when y, predicted, not predicted, the actual value is 0. When you expand that one also, you get a similar term. Okay, so what we are trying to say is you can write this whole formula in this way. So if you see closely, this is what you get, and then you're putting a yi over here. Okay, so you're able to put yi because now instead of 0, 1 representation, you are using -1 representation. So there are 2 ways. Please note this. If you represent negative class as 0 and positive as 1, and the other cases you represent negative class as -1 and positive class as +1. So these are 2 different scenarios. Now, you started with this one. So this is the formula that is used with 0, 1. You start with that formula, which is this one. You start with this one. And then you expand these terms. In first case, this one. In second case, this one. To end up with this. Okay. Now you see, if you don't use 0, you use yi is equal to -1 and you put a yi over here and put a minus sign here, then this term becomes equal to this term. So when the classes are represented as -1 plus 1, you use this representation. And when the classes are represented as 0 and 1, you use this representation. That's all we are saying here. So these are 2 different representations of logistic loss. Okay. Okay. So that's what we are asking here. S1 is a scenario.
Logistic.
Yeah.
If you can go back to the equation. Yeah. Is there any assumption in this equation?
Assumption is in what kind of assumption?
Can y hat be value 0 or 1? Can it happen?
Y hat, so okay, y hat will be 0. What is y hat? Y hat is, so this is y hat. So this y hat is actually sigmoid, isn't it? Y hat is sigmoid of W transpose X, right? And if you see the sigmoid, right, okay, this is bad. Something like this, right? This is 0.5. This is when W transpose X is equal to 0, this will be 0.5. And when this is huge, if you see these don't touch 0, right? This doesn't touch 0, this doesn't touch 1, right?
Yeah.
That is why.
That
So
means y hat cannot be 0 and 1 equal
not
to.
exactly, it will be close, it can be close, and that too it will be close when when W transpose X is huge value. Okay, so
Okay.
it never touches 1, so it's like this, it never touches 1, it never touches 0, right?
Yes.
So that issue that you're thinking of taking log of
Hmm.
something 0, it will not happen. Okay. Okay. So that's what we are asking here. S1 is a scenario where the classes are represented by 0 and 1, and S2 is a scenario where classes are represented by -1 plus 1. So which of the following would be appropriate loss function? As we just now discussed, in the first scenario, this loss function, minus y log y hat, -1 minus y log 1 minus y hat. And the second one will be log, there's only one representation, doesn't matter if the class is 0 or 1. Not 0, 1, doesn't matter if the class is +1 or -1, right? Log of 1 plus e to the minus W transpose X. Okay. Okay, so moving on. Now, perceptron, if you study, its loss function, if you remember, the loss of perceptron, what is the loss, what is the update rule of perceptron? Does anybody remember? Forgot? When do we update the weight? Right? Perceptron, there is an algorithm, right, that we did. What we do in each iteration, we check whether a given data point is being predicted correctly by our W or not. If it is being correctly predicted, we are fine, we'll move on to the next data point. If it is not being correctly predicted, we update the value of W with this update rule. The new W will be equal to old W plus xt into yt, where xt is the data point on which the mistake happened and yt is the actual y value. So this is the update rule. Now, what is the update rule in gradient descent? Can anybody remind me?
Wt minus eta.
Very good.
Del of gradient.
Gradient of?
Gradient of the
Loss
point
function. Loss function, whatever the loss function is, right? Gradient of loss function at Wt. Yeah. Okay. So if you compare these two formulae, let's say I put eta is equal to 1. Okay. Then this becomes Wt minus gradient of loss function, right? Now, if you compare 1 and 2, you see that if you compare these two terms, right, this is what you get, which means that the gradient is equal to minus xtyt, right? This is what you get, which means perceptron, if you look at it in an alternate way, you see that you're actually sort of performing a gradient descent where the gradient of the loss function is equal to minus xt into yt, right? Now, if you look at the hinge loss, I want to show this, let me not repeat the same thing, so I'll show this to you. So if you look at the hinge loss function that we have already seen, which is equal to max of 0 comma minus W transpose X into Y, right? And this is red one is your hinge loss, right? As you know, this is this is not differentiable at this point, right? And when some function is not differentiable at a point, what do? What can we use? We can use subgradients, isn't it?
Yeah.
So they can be, as you might know, at this point, there are several subgradients possible. The green lines represent the subgradients. There can be multiple such lines. We can choose any one of them. Okay. Now, this is the loss function of hinge loss. When you take the gradient of this with respect to the weight, so when W transpose X into Y is less than 0, what happens? When W transpose X into Y is less than 0, which is negative, this becomes positive. This becomes positive, and we are taking the max of that, which means that positive value will be the value of the loss. This value, right? This value. Now, when W transpose X into Y is greater than 0, what happens? When W transpose X into Y is greater than 0, which is positive, negative of that will be negative. So the max of these two values will be 0. So the loss will be 0, which is representing this part. Okay, I hope this part is clear. Now, in order to, so since this is a piecewise function, right? This is one piece, this is another piece, and they are joined. If you want to find the gradient of this piecewise function, you will again do that piecewise. So the gradient of this particular part. So in one case, this is the loss, in the other case, this is the loss. So in this one case, when this is the loss, the gradient with respect to W is going to be minus xy, right? And in this case, as you can see, the gradient will be 0, right? So that's what we are writing here. And at this very point, there are several subgradients possible, and the slope, the gradient of the subgradient that you will choose, the derivative of the subgradient that you will choose at this point will be somewhere between these two values, minus xy and 0. So you can write it like this, somewhere between these two values. Okay. Now, getting back to what we derived here, minus xy, we could have chosen any value between minus 1 and 0, let's say 0.5 into xy, minus 0.5. So minus 0.5 into xy we could have chosen. That could have been possible as well. That could have been a valid choice as well. Now we see that perceptron chooses minus xy as the gradient. Okay. So you can see that hinge loss, you can see that perceptron is actually a special case of hinge loss, okay, where perceptron chooses to have that subgradient at this point, which has a slope minus 1 into xy, right? So that way you see that perceptron is equivalent to a hinge loss as a special case. Okay, getting back here. So what are the values of step size eta and the gradient of loss function? So we have just now saw that eta we are taking 1, right? We have taken eta to be 1, and that's how we reached here, and that's how we reached here. Now when you put minus xy as the gradient over here, you put minus xy here, then this becomes positive. This is 1, so this becomes positive, and that's how we get the perceptron update rule. Okay, so the gradient that we are taking is minus xy. That's what we are asking here. Eta is 1 and gradient is minus xy. Okay, so this is the correct option. Next one. Which of the following represents the loss function for boosting? So boosting, actually we have covered sort of at a broad level. So anyway, so the loss function that boosting uses is exponential loss, and that is e to the minus y into hx, or in other words, e to the minus w transpose x into y. So that's the loss function that is used in boosting. And next one, hinge loss is convex but not differentiable, right? So we have seen what is hinge loss. This This is hinge loss. This is convex. Yeah, that's true. But it is not differentiable. So we say that a function is differentiable if it is differentiable at all points, but it is not differentiable at one point. So we'll say it is not differentiable. That's other thing that we can use subgradient, but yeah, as we see, this is not differentiable. Okay, so the next one, the loss function of neural network is a convex function. So in neural networks, as we know, there are several layers, right? So this is the input layer, this is hidden layer, and this is the output layer, right? And on every, so these are the different neurons, and on every neuron, at every neuron, we have an activation function. So basically the loss that we get, so what are we asking here? The loss function of a neural network is a convex function. So the loss function that we get, one moment, sorry. Yeah. The loss function that we get, so in case of regression, we'll be comparing this W transpose X value with the actual Y value, right? And we'll compute the squared loss. Now, what is W transpose X? W transpose X will be getting from this W1, W2, WD, and these weights will be multiplied by whatever we get over here. And what we get over here is dependent on what are the weight values in the previous layer. So this will be a better diagram. So here, whatever we get, W transpose X, we'll compare that with the Y value. Let's say we are talking about regression, and we're computing the squared loss of that, squared error of that, right? Now, what is W transpose X? How do we get that? Let's try to understand that. The W transpose X, so what are the X values? W's are these weights. There are weights on every edge, right? Now, what are the X values? The X values are the values which are produced by these neurons. And how values are produced on these neurons? They are dependent on the values that are produced at the previous layers. And then previous layers have further weights. Other than that, there are also activation functions at each layer, okay? So the resultant loss function that we get is indeed neither convex nor concave. So you know how the sine function is, right? It's neither convex nor concave. So similar is the kind of loss function that you get for neural networks. So it is not a convex function. So if you apply gradient descent, you get some result, but that may not be the global minima. So whatever result you get has been found to work well in practice, although may not be the optimal one, but that's fine. Well, there's some configuration mistake here. The answer should be false. I'll get that fixed as well. I think there is, yeah, this is true, which is incorrect. I don't know how this issue, this mistake crept in. The correct answer is false. Okay, for a data set containing 10 features, how many neurons will the input and output layers respectively have in case of a regression problem? So in neural network, the number of neurons in the input layer, let me call them F1, F2, so as to not confuse you with X1, X2, because we've been using X1, X2 for the data points, right? So far, that's how we have been using. X1 is data point 1, and this is a vector, right? That's how we've been looking at the terms. So let me use F1, F2 here. So if there are 10 features, there'll be 10 neurons in the input. This is the input layer. And then there'll be some hidden layers. There'll be some neurons in those hidden layers, and there'll be an output layer. In case of regression, there'll be one neuron here. Here there'll be, let's say there are 2 hidden layers. So this is how, this is input layer. So this F1 will be connected. So this is a fully connected one that we are talking about. There are several variants of neural networks. For now, we'll look at fully connected one. So F2 will be fed as an input to each of the neurons in the next layer, and so on and so forth, right? So that's how it will happen, right? Again, this will be connected with all the further neurons. Sorry, like that. And this one will be connected here. So here, what are we asking? 10 features. So, like I told you just now, there'll be 10. How many neurons is what we are asking? So there'll be 10 neurons in the input layer, and it's a regression problem. So there'll be 1 neuron in the output layer. Okay. So 10 into 1 should be the correct option. Which of the following may not be an appropriate choice for the activation function to be used for the hidden layers of network? So, you know, we haven't gone into the details of the back propagation algorithm, which is used to find the weight. So, as we know, there are weights at every edge. There are some weights, right? I will not use the subscripts. Just know that there are weights to be computed for each edge, right? How do we do that? That's done using back propagation algorithm, which precisely computes the gradients, the rate of change of the function. When you change, when you make a small change in this weight, how does your output change? So you initialize some weights, right? That's the first iteration. Based on those weights, you get some let's say y hat, you get some predicted value, you compare that with y value, get some error. In case of regression, you get some squared error, so you get some value here. Now based on this value, you want to change the weights. Now how much you should change and which weight should you change, that is decided by the back propagation algorithm, where what we keep track of is how much change in this quantity happens if we make some change in this weight. How much change in this quantity happens if you make some change in this weight, and so on. That's what we keep track of. And based on that, we update the weights. And so we update the weights, that's a back propagation. Then once again, we use those new weights and we have another forward pass. This is called forward pass, this is backward pass. In forward pass, once again, we'll get a new value. This y hat will be an updated value. We'll get another updated value, and then once again we'll see how much change we should make in W to reduce this, right? We will update our weights. So again, this is precisely gradient descent that we are using, but earlier we were having only W1, W2, let's say. If there were 8 features, there'll be up to W8. But right now, there are many weights that we need to compare. We need to compute for every edge. So there are many parameters that need to be computed. One more thing that we should also note is that there is a bias associated with every neuron. That is also something that you should note. Every neuron has some bias also, right? For example, in linear regression, what do we have? W transpose X plus, not this. Let's say there is one feature, so W1 X1 plus W naught. This W naught is a bias, right? We are calling this B here. You can use any term. So if you know that if B is not there, then the prediction, the line will pass through the origin. If you want to be able to have some intercept, then you better give the value of W naught as well. The same thing is happening here. You give a value of bias. So there's one more parameter that is to be computed here. Okay, so that's another thing. Getting back. Yeah. So like I said, how do we compute these weights? We compute these weights using back propagation, which involves gradients, right? So we need to be able to differentiate the given function. But if on some hidden layer, we are using some activation function which is not differentiable, we will not be able to apply gradient descent, right? Makes sense? So So 0, 1 loss, if we use in some hidden layer as an activation function, since we have seen 0, 1 is not a continuous function, so definitely it is not differentiable. So we cannot use this function. This is not an appropriate choice. Okay. All right. The values, these values will be transformed to which values using ReLU function, which is rectified linear unit. What is rectified linear unit? So there are several activation functions that we can use. So what are activation functions? So activation functions simply transform the values of the values that are produced by a model to some other range. We can decide which range we want the values to be transformed to, and accordingly we can choose different activation functions. For example, in logistic regression, the kind of output that we were getting was real, right? And it was a classification problem. So we wanted to reduce the values between 0 and 1, which could be used as probabilities. So we used a sigmoid function because we know that the values, the output of a sigmoid function always ranges between 0 and 1, right? So that was an appropriate function there. So we didn't use the term activation there, but it's actually a kind of activation function. There are several other activation functions that are used in neural networks. So other than sigmoid, there is ReLU. As you can see, this one is ReLU, rectified linear unit. So what it does is, if the value is negative, if the value produced is negative, it will make that 0. Right? If the value produced by some neuron is negative, it will convert that to 0. And if the value produced by some neuron is positive, it will let it be. That's how a rectified linear unit function works. So this is a linear unit. Rest all is 0. Okay, so can be represented as max of 0 and the value. Right? If the value is negative, you get a 0. If the value is positive, you get that value. So if these values are passed to ReLU, what will be the output? As you know, negative values are transformed to 0. So we will be getting 0, 20, 30, 0. This one. Okay. All right. So this, let's move on to the next one. If activation functions are not used in a linear, in a neural network, it will be equivalent to So I told you that at every neuron there is an activation. So this is the value that is produced. So let's say Z is the value that is Z1 is the value that is produced at this neuron, and then we will apply some activation function to this Z1, and that will be sigma Z1, and that's what is passed on, right? Let's say we do not apply this. So in that case, this Z1 will be further passed on here. So basically, what we are doing, if there is no activation, what we eventually are doing is there's some weight, this F1 into some weight, and then F2 into some weight, F3 into some weight, F4 into some weight, right? And we get Z1. And then Z1 is passed here, and then some weight is further multiplied with that Z1. And then some other weight is further multiplied with Z1. That's what is happening. It's just different weights which are getting multiplied with the feature value, isn't it? That's what is happening, right? So it basically becomes equivalent to linear regression, right? There's no transformation of the values that is happening. It's just different weights being multiplied with different feature values, right? W1x1 plus W2x2 WDXT. This is what we do in linear regression. So here also a similar thing is happening. It is that weights are coming in different components, and that thing is getting multiplied with the feature values. So if activation functions are not used, then it is equivalent to a linear regression. A complicated linear regression is what you can say. which will be of no use. Rather, you can use simple linear regression. Okay, backpropagation is a technique of computing model parameters that always produces global minima. So I told you the loss function in neural networks is not convex. Hence, so backpropagation involves using gradient descent. Since the loss function is not convex, then that gradient descent will not be able to produce, will not be able to reach the global minima. So backpropagation computes model parameters, but that may not be global minima, that may be local minima. So this is false. Next one. Which of the following loss functions are appropriate to be used at the output layer for classification and regression? So I told you, right, in case of classification, if it's a binary classification problem, then you will use logistic loss, binary cross entropy loss. You can also call logistic loss. So binary cross entropy loss is what you use in case of binary classification. If it is in general classification where number of classes could be any, then cross entropy loss is what you would use. So cross entropy loss is just the generalization of the binary cross entropy loss. Cross entropy loss, you can write minus sigma of, let's say there are k classes, I goes from 1 to k, yi log yi hat. Okay, so yi is the value, actual value corresponding to the first class. So in case of multi class classification, the output will be something like this, right? If there are 3 classes, 1 0 0, and let's say your model produces something like 0.3, let's say 0.8, 0.1, 0.1, right? So this is what you have to compare here. So this is your yi, I mean y1, y2, y3, and this is your y1 hat, y2 hat, y3 hat, right? So all these values you will put in here. So you'll get something like minus yi log yi hat, minus yi log yi hat, minus yi log yi hat, right? So this becomes 0, this becomes 0. This is the value that you will compute. That will be the value of cross entropy loss. So this, as you can see, it's a generalized form of binary cross entropy. In binary cross entropy, we had 2 of these terms. Now we can have a k number of terms, right? Yeah, so cross entropy and square loss is what we'll be using in the output layer. Let's move on to the practice questions now. So this is the data that we are given, and in the first question, we have to compute the value of 0, 1 loss, right? And we are given W0 and W1. Okay. Now, what is 0, 1 loss? We compute the value of W transpose X. We check its sign. If the sign matches with the actual sign, which is either +1 or -1. If the sign matches, we give a 0 error. If the sign doesn't match, we give a 1 error, right? That's 0, 1 loss. So here X is given, right? So what you will do is you will compute the value of W transpose X, right? So what is given? X is given. And Y is given to be plus, plus, minus, minus, right? And we are given W0 1, W1 1. W0 1, W1 is given to be 1. Now, we know what is 0, 1 loss, but it is given as well. Y hat is equal to sine of W transpose X. Okay. So W transpose X, if you have to compute, what is W transpose X? W1 x1 plus W0, right? Here this is x1. W1 x1 plus W0. So you multiply, W1 is 1. You multiply this with 1, add 1. 1, add 1. You multiply this with 1. Let me write this down. Multiply this with 1, add 1. Minus 1 plus 1. Minus 3 plus 1. Minus 2 plus 1, right? And that is 2, 0, minus 2, minus 1, right? Now, in 0, 1 loss, we look at the sign, right? The sign is plus 1. Greater than equal to 0 is plus 1, right? Minus 1, minus 1. The sign is matching in all cases. So the loss is going to be 0, right? So the 0, 1 loss for this particular data is going to be 0. The answer will be 0, right? Next one, what is the value of squared loss? What is y hat? Y hat is W transpose X. W transpose X we have already, this value, these values. This is W transpose X. W transpose X minus Y is what we have to do. For this loss, use Y is equal to 0 wherever Y is equal to minus 1. So this is the Y that we have to use. So W transpose X minus Y. W transpose X minus Y, right? What will that be? W transpose X minus Y, 2 minus 1 and then square of that. 0 minus 1 square of that. Minus 2 minus 0 minus 1 minus 0 square, right? How much this is? 2 minus 1, 1. 1 square, and this is 4, this is 1, right? Total will come out to be 7. Okay, so this is the loss for, this is a squared loss for the same data. Okay, what is the value of hinge loss? And this is also given, although it will be good for you to remember this as well. Max of 0 in 0 and 1 minus W transpose XY. Okay. Yeah, this is W transpose X as we know. Max of 0 and W transpose XY. Let's compute that. W transpose XY. This is W transpose X and this is Y. This is Y that we have to use. This one and this one, right? W transpose X into Y, that is 2, right? And this is 0 and this is 2, right? W transpose X into Y, 2, 1, right? This is what we get. Now 1 minus W transpose XY. 1 minus W transpose XY will be 1 minus 2 minus 1. 1 minus 0, 1. 1 minus 2 minus 1. 1 minus 1, 0. Max of 0 and this. Max hinge loss, I'll write. Max of 0 and this 0. Max of 0 and 1, 1. Max of 0 minus 1, 0. Max of 0 and 0, 0. Right? So the total is 1. This is the loss that we are getting through hinge loss. Right? This is 1. So earlier we discussed what could be a good surrogate function for 0, 1 loss, right? So if you see the 0, 1 loss came out to be 0, right? And the squared loss for the same data came out to be 7. And the hinge loss came out to be 1. So you see that this 1 is most closely, I mean, quite close to 0. But 7 is huge. I mean, it could actually have gone even more than that given the data, right? So you get an idea. But hinge loss mostly stays near 0, 1 loss. Okay. All right. So next question. Given a cat image, you want to classify which of the 10 cat breeds it belongs to using a neural network. Right? Which loss function will be appropriate? Okay, we just now discussed. It's a multi-class. So what will be the correct answer? Anybody would like to guess? I've been speaking on and on, so I just want to check if people are there. So it's a multi-class classification, right? So what will be appropriate here? Yeah, right. Cross entropy loss. I've just now explained to you. So it's a multi-class classification problem. 0 and loss definitely is not a good one. Is not differentiable. Square loss we've seen is not a good one. Hinge loss, again, it's a multi-class classification. We'll be using cross entropy loss. Okay, next one. These values are given to us. These are the actual values and these are the predicted values by the model. Now, what will be the value of the cross entropy loss? How would you compute that? I've actually, told that to you. Can anybody point out how do we do this? Just now I told you the formula for cross entropy loss, right? This formula, right? This
Y
formula.
minus y.
Sorry?
Yeah,
No,
yeah.
no. This one. This is a classification problem. This is what is actual y vector. And this is a 3-class classification problem, as you see. And this is the vector that is produced by our model. Right, 0.7, 0.2, 0.1 are the probabilities that our model has generated. And we have to find the value of cross entropy loss. We've actually done that just now. This is the formula that we'll be using. So cross entropy loss minus sum of I goes from 1 to 3 in this case, y I log of yi hat, right? This is the formula that we'll be using. So minus so 1, 0, 0 is our y, and what is our y hat? 0.7, 0.2, 0.1, right? This is what is given. So just the same way, minus y log y hat minus y log y hat minus y log y hat. This becomes 0, this becomes 0. We end up minus log 0.7. You can look up the value of 0.7. Will be some negative value, negative, negative, positive, some positive value will get less than 1. Okay, you can just check that out. So that's the correct answer. Next one. Following is the output produced by an activation function at some hidden layer of a neural network. Which of the following is definitely not the activation function? Would somebody like to tell me? Okay, sigmoid we know, right? What is the range of values that one moment. Not the activation function, 0. Right. Yeah. What is the range of the output that we get from sigmoid? Can anybody tell me?
0, 1.
0 to 1, right? Sigmoid produces a value which is between 0 and 1. Okay. So can sigmoid be... So this is what we are... this is the output produced by an activation function. Can this kind of output be produced by sigmoid is what I'm asking you.
No, no.
No, right? Why?
Because the output is 0 or 1. No?
Right. So there are values more than 1 also. So this is not correct. Okay, tan h, if you know, this is another kind of activation function, and it produces values between -1 and 1. Okay. This is another activation function. So sigmoid produces between 0 and 1, tan h produces between -1 and +1. Okay. Can this be... Okay, I think I need to fix this question. Okay, I'll see that. We'll see that in a while. Okay, can this kind of output be produced by something like tan h?
No.
No, right?
Yeah.
Because tan h produces between -1 and +1, and these values are outside that range. Okay. Can this kind of output be produced by ReLU?
ReLU, ma'am, can you explain ReLU?
Yeah, what does ReLU do? I'll show you. So if it is negative, it will make that 0. So this is ReLU. If the value is negative, it will make that 0. If the value is positive, that will be as it is, which means there are no negative values as a result of applying ReLU, isn't it? Every negative value is transformed to 0, right? So there are no negative values.
Okay.
So I think I should change this. But you should understand that's the motive. I'll fix this question. Apparently, none of these can be definitely the activation function, right? ReLU cannot be because there are negative values. Sigmoid it cannot be because sigmoid produces between 0 and 1, and tanh it cannot be because tanh produces between -1 and +1. This needs to be changed. We'll check that. Next one. Consider a neural network with 3 inputs, 1 output, right? There are 3 hidden layers, each with 3 neurons. How many parameters need to be learned by the backpropagation algorithm? Right? Assume that each hidden and output layer neuron also contains a bias. So this is the scenario. 3 inputs. Let's say x1, x2, x3. Sorry, I'll use f1, f2, f3. f1, f2. One output, right? One output. There are 3 hidden layers, each with 3 neurons. 1, 2, 3, 1, 2, 3, 1, 2, 3, right? How many parameters need to be learned by the backpropagation algorithm? Each neuron has a bias also. Okay. Now, how would these things be connected? This F1 will be connected to each of the 3 neurons, and so on. Right? Again, here will be another fully connected one, right? Again, here will be another one. So the question is, how many parameters need to be computed? Would anybody like to answer that? Any ideas? So I told you that each edge will have a weight, right? There'll be some weight here, there'll be some weight here, there'll be some weight here. At each edge, there'll be some weight. Now, how many edges there are? Can you tell me? How many edges there are here?
Here is 9.
Yeah. How many here?
Again 9.
Again 9. How many here?
9.
9, and here
3.
3, right? So 9 plus 9 plus 9 plus 3. That should be the total number of parameters that the backpropagation algorithm should compute. Yeah? We are also told that there is a bias also, right? Okay. Which means at each neuron, there will be one more. That W naught or B that we spoke about. Okay. W naught dash, W naught double dash, whatever. I mean, I want to just tell that they are different. So each neuron has the bias also. So 9 plus 9, 27, plus 9, 27, plus 3, 30, right? Now let's compute the bias. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 neurons. So one bias at each neuron. So that makes 40. Okay. So in total, 40 parameters need to be computed. Is that clear? Okay. Next one. Which of the following are true?
Ma'am, just one question. In question number 7.
Yeah.
This is the neuron to neuron connection you have shown. It is the maximum number. Is it possible that some of the neuron not get connected with?
Yeah. So, like I said, this is a fully connected neural network that we are looking at, but there are several variants of that. So, some of the weights we actually make 0. There's something called how to handle regularization in neural networks. So there we drop out. There's something called dropout where we make the weight 0 for some of the edges. So there are several strategies that we do. Like Sir said, you will learn it in the next course, which is on deep learning. But what you should note at this point is we are looking at fully connected network here, but several variants are there where the nodes are not completely connected.
Now, if the question is like that, then by default, should we consider this?
By default, you will connect. By default, you will consider fully connected. Yes. In any question, you will completely connect it.
Okay.
Yeah. Okay. So this question is on sigmoid and softmax. So sigmoid you are aware of, right? Sigmoid function you're aware of, 1 over 1 plus e to the minus z, right? Sigma of z is equal to this. And it gives you values between 0 and 1, right? Between 0 and 1. Now, if this is used in case of binary classification. In case of a multi-class classification, you actually use a generalized version of sigmoid, which is called softmax. Softmax is, let's say S denotes the softmax. So in case of a multi-class classification, there will be multiple values, right? Here there was one value that you had to transform between 0 and 1. In case of multi-class classification also, if you use this sigmoid function, you will get a value between 0 and 1. But in case of multi-class classification, what else we want is the sum of those values that are produced should be 1. If you use sigmoid at every point at the output layer, if you use sigmoid, you get some values between 0 and 1, some values between 0 and 1, and so on. But the sum will not be 1, which is not what we want. In case of multi-class classification, we want the output probabilities pertaining to different classes such that the sum is 1. So in that case, we use softmax, which is a generalized version of sigmoid, which is e to the xi divided by sum I goes from 1 to k if there are k classes. Yeah, so let me finish this first and then we'll see the question. So this is the formula of softmax. So let's say you have some values, let's say 2, 4 and 5, let's say. Now if you apply sigmoid on 2, you get some value. If you apply sigmoid on 4, you get some value, and so on. But the sum we want to be 1. So in that case, we'll use this softmax function where the probability pertaining to 2 will be e to the 2 divided by e to the 2 plus e to the 4 plus e to the 5. The probability pertaining to 4 will be e to the 4 divided by e to the 2, e to the 4 plus e to the 5. So the denominator is same for all, as you see, right? So the result is that whatever values are produced by these, the sum is equal to 1. So that's your softmax function, which is used in multi-class classification. Now let's see these options. Both sigmoid and softmax are activation functions, yes. Sigmoid is used for binary classification while softmax applies to multi-class. Softmax is an extension of sigmoid. Sigmoid is also called logistic, we know that. Both functions transform a real value to a number between 0 and 1. So all these are correct. Okay. So yeah, these were practice questions for you. This one I'll fix, and yeah. So the deadline of graded will actually be updated to 1 moment. Days. This is second, right? So this will be updated to, I guess, 4th. We'll do that. 4th December. Okay. So I hope this was clear. So how many of you have watched the lectures once again? If I because nobody was asking questions, so I wanted to know. Nobody. Yeah, you watched only few, like you told. Others, did you watch, or are you yet to start watching? Okay, never mind. So
No,
please watch.
ma'am, didn't watch it.
Okay, no problem. So please watch the lectures and then solve the graded. In case of any doubt, please post it on Discourse, and we'll take it from there. Okay.
Ma'am, are
Any
there any revision sessions lined up next?
revision sessions for final exam?
As
You're
in
asking?
for the whole syllabus?
Final exam?
Yeah.
Yeah, yeah. Final exam will have revision sessions. Yes. Yeah. Any other thing that we should discuss? Are we live, by the way? I don't see live streaming. Oh, we are. We are. Okay. Okay. Yeah. Any other thing that we should discuss? Okay, I guess you should watch the lectures and then only you'll be able to ask questions. So please watch them and solve your graded assignment. I think I've given you pretty much good idea of the things that would be required for you to solve the graded assignment. So you should be able to do that. Just in case there's some doubt, please ask it there, and we'll take it. Okay, then thanks everyone. We'll see you some other time.
Thank you.
Okay, thanks everyone. Bye.